I want to try and pick up where we were talking about last time, and that was the we were doing the product construction for the intersection of two languages. I don't know if you remember this, but this was about the intersection of languages, regular languages, right? And the idea is you have two DFAs and you want to combine them together to make a DFA for the intersection language. That is to say, you make a new DFA which accepts everything that was accepted on the first one and also the second one. So you start with two machines, make a new DFA for that does kind of both of them at the same time. Let's just try one more example to make sure we still remember how to do this. I don't know if this is what you've been thinking about all weekend. Probably not. But it's not so hard to do. It's just you got to keep straight. So I'm going to write a DFA over here, which has 4 states, A, B, C, D. I'll make A and D the accepting. This one I just sort of made up. I don't intend for this to represent anything meaningful, although if you want to, you could try and think about what is the language accepted by this DFA, but it's not necessary to understand it. I'm just writing it down. Okay, so this is my DFA. By the way, here on the Zoom, you should probably keep yourself muted, but if you do have questions, feel free to shout them out, just as usual. Okay, so that's the first machine. I'll call this one M1. And then I'm going to have another machine, and my goal is to combine them together into a single kind of big machine using what we call the product construction. So this one is just 2 states, S and T. And let's say arrows go like this. Like so. All right, this is M2. Those are my 2 machines. Actually, I'm going to move this over a little bit. I want to be able to scroll and not go behind my beautiful face like that. All right. So these are my 2 machines, and I want to combine them together into a single kind of big machine, which does the same thing that these 2 does. That is to say, on my new machine, I want it to be accepted when it is accepted on both of these original ones. And the way we do that is by combining things together in pairs. So the states in my intersection machine, this is called the product construction. That's product because in set theory, the word product refers to making pairs out of things. The product construction. You make a new DFA where the states in my new one are pairs of states from the original 2. So I'm going to just start with the pair of the starting states. So I choose one state over here and one state over here. And you might as well just start at the starting state, which is this starting state, comma, this starting state. And then draw arrows to new states just according to when you need them. So from here, I need to, this is going to be the starting state in my answer. I need to have an A arrow and a B arrow. And the way you decide where does it go, let's think about the A arrow from A, comma, S. You think about where does the state A go when I do the letter A? It becomes a B. And then where does the state S go when I do the letter A? It stays a S. So this AS, the big A turns into a big B. The big S stays a big S, so it becomes BS. And I'm going to put that one over here. It's like that. All right. A comma S becomes B comma S. That's because in the original machines, when you do the letter A, the big state A becomes state B, and state S stays like it is. All right. What about the letter B from here? Okay, so again, I do the same thing. A comma S, state A becomes a C, and state S becomes a T. So A comma S becomes C comma T, and I will make that down here. And I'm just going to fill in the states kind of as we go. Every state down here needs to have 2 outgoing arrows. Now this one already has 2 outgoing arrows, so I'm done with this state. But I have to see, where does this one go to? Where does this one go to? In theory, I could end up with a maximum of 8 states down here. That would be every possible pairing of the 2 original sets of states. But hopefully I'm not going to actually need to use all of them, but we'll see. BS, let's do that one. The A letter from BS, state B becomes C, and state S stays like it is. So this, the A letter, becomes CS. Whoa, sorry. Come on. CS, like so. And then from BS, the B letter, the state B becomes D, and the state S becomes T. This becomes DT, which I will put down below. I did this ahead of time, and I decided ahead of time the most convenient way to position the states in the answer. All right, we keep going. Okay, so this one is handled. How about this one? Where do my arrows go from C, comma, S? Anybody want to tell me? Can somebody shout out where should the A arrow go from CS?
Is it back to... Sorry, you go.
I heard DS from somebody. I think that's correct. CS, the C becomes a D when I do A, and the S stays like it is when I do A. So CS becomes DS. Am I right? Yeah, somehow I did that wrong on my paper.
Professor?
Yes?
What about the A's going between C and B? Or, yeah.
Oh, yeah, maybe that's... Yeah, this is bogus right here. I don't know what... I have a C outgoing A and another outgoing A here. Sorry, that's why I just said I must have done this wrong on my paper. You can't have 2 outgoing A's. It's that COVID talking. This is not allowed on a DFA. Sorry about that. So we have to erase one of them. I think actually it didn't make a difference until just now. So let's get rid of this one down here going to the D. So that's why I did it differently on my paper, because this is bogus. Okay, I just erased that A right here. Sorry about that. Thank you for noticing. It's actually not immediately obvious that I messed it up, but definitely did. So that changes the answer here. C becomes a B when I do A, and then the S does stay like it is. So this becomes BS. It goes back to there. So it's like that. And this is what I had written on my paper. Thank you for that. All right. Okay, let's continue from here. What about B? When I do the letter B, C becomes D, and S becomes T. That becomes DT, which is like that. All right. So this state is now handled. We just need 2 outgoing arrows from every state. This one is also handled. How about, let's go down to C and T. Where does that go? When I do A from C, it goes to B. And when I do A from T, it goes to S. So that goes to BS, which is up here. From CT, when I do the letter B, C becomes D, and T stays like it is. That becomes DT. So it's here. And I think we're almost done, hopefully. This DT, I need 2 arrows from DT. The A arrow from DT goes back to D and to S. This goes to DS, which unfortunately is not here, so I have to make a new one. That's the A arrow from DT. And then I also have the DT with the B arrow. It's D and T. So this B arrow is a loop back. All right. I think we're almost done here. How about states for arrows for DS? You know, in the worst case, we're just going to keep on getting new states. We might not be almost done, but hopefully. D comma S. When I do A, it stays as a D and stays as a S. So this is like that. And when I do B, D stays a D, and this goes over to T. D, T. That's back here. All right, and now I think we're done. Every state has 2 outgoing arrows. All right. Two little things that we need here just to finish. We're not totally completely done, and that is not two things, just one thing. You need to indicate the starting state, but I already did that. The starting state in the product is always the whatever the pair of the two original starting states. And then you also need to indicate the accepting states. What are the accepting states? Well, remember the whole point of this machine here is it's supposed to accept any strings which are accepted in the first machine and also in the second machine. Here's another typo, sorry. Did anyone notice there are no accepting states in the second machine? It's not relevant until now, but I meant for the T state to be accepting. Sorry about that. So anyway, what are accepting in the product machine should be anything which is accepting on the first one and also the second one. That means A and T are accepting, and also D and T has to be accepted on the first machine and also the second one. So the accepting states in this machine are A and T, which is not even on my machine, so I don't need to care about that. And also D and T, which is right there. So D comma T is accepting, all right? And maybe I'll just indicate, so parenthetically here, A comma T would also be accepting. But we didn't use it, so it doesn't matter. It is sort of, that's sometimes called an unreachable state. Technically, you could say it is a state in this machine, but you just can't get there from the starting state, and so you don't even have to write it down. It's irrelevant. All right. This is what we call the product construction for the intersection of two languages. Anybody got any questions about that? It'll take you a few minutes to work out the details, but the idea of it, I think, is pretty straightforward. Any thoughts about that? All right, I want to try to write down formally what this construction looks like. So what does it look like? What does it look like formally? Remember, this formal thing is describing the DFA as a tuple of 5 things. The M, sigma, delta, Q naught, and F. I don't know if you remember the details of that from last week, but I will refresh our memory. What does it look like formally? We start with 2 machines, which I call M1 and M2. Now I'm going to write them as Q sigma. I'll call this delta 1, Q0, and F1. And then the second one, the second one is going to be, different. I'm just going to use different symbols for everything in the second one. So I'm going to call the states are R. So R is the set of states in the second machine. The alphabet of the second machine, actually, if you were paying attention, if you think about it a moment, you will realize this only makes sense if the 2 machines are using the same alphabet, right? In the example, it was A's and B's both times. So when you're doing this construction, the 2 alphabets must be the same. You don't try to combine as a product 2 machines. The point is we're trying to get the intersection of the 2 languages, and if they don't have the same alphabet, that doesn't make any sense. All right. Anyway, the transition function, I will call this one delta 2. Remember, that represents what the arrows look like. And then Q0 was the starting state of the first machine. This one I'll call R0, just because the states here are called R. And then the set of accepting states I will call F2. Accepting states for the second machine. All right. Can we write down, in terms of the set theory, what is the new machine which is created by taking the product, this thing that we just did, the product construction? So I'm going to say then the product construction creates a new machine can we write down, in terms of the set theory, what this new machine actually looks like? Like, what is the set of states in the product? Remember the way that we write down what the states are? Like these ones. What are they? They are pairs of states from the original two machines. They are pairs where the first thing is from Q and the second thing is from R. And actually there's the simple way to write that in set theory is just Q cross R, right? This is, after all, why it's called the product construction, because the states in the new machine, the set of states in the new machine is the product of the set of states from the original two machines. Okay, what about the alphabet in the new machine? Anybody want to shout it out? How do you get the alphabet of the new machine versus the alphabet of the two machines we started with? You just have to think, do you have to, is the alphabet made up of pairs? Or is it the same alphabet or what?
Is it the same alphabet?
I believe it is the same alphabet. If you just look at the machine here, you will see all the arrows are labeled by A's and B's. So the alphabet of this machine is still A's and B's. All right, so it's like so. Sigma here, right? It's still just A's and B's or whatever the alphabet from the original machines were. It's still, that's still the alphabet of the new machine. Okay, and then the transition function, this we need to say a little bit more in detail with, so I'm just going to write it as delta for now, and then down here I'm going to say where delta, blah, 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 blah. So I will explain the delta later, because that's, as usual, the delta is kind of the most complicated part of it. What about the starting state? In terms of the set theory, you have to say what state in the product am I going to start with, and it should be written as a pair, because the states in the new machine are pairs of states from the original machine. Anyone think you can say? I'm about to write a pair here that should represent the starting state.
Would it be Q naught, R naught?
Yeah, it's a pair Q naught, comma R naught. That's where you start. This is what I said when we were drawing this picture here. How do you decide where to start over here? It's the starting from this one and the starting from this one. So it is the pair Q naught, comma R naught. That's the original, the first starting state paired together with the second starting state. And then finally, the accepting states. Here I want to see the set of accepting states in the product here. Now in this case there were two of them. One is kind of invisible on this diagram, but remember we want the set of all things which are accepting in the first one and also accepting in the second one, but paired together. All right. Anybody see how you could do this with the set theory? Based on, I mean, it's somehow based on F1 and F2. You might be tempted to say, although this is not correct, you might be tempted to say F1 intersect F2, but actually that's not, you can't do that. I know what you mean when you say that, but and I think your heart is in the right place, but F1 and F2 are not sets which you can take the intersection of. Like in this example, F1 is A comma D, and F2 is T. The intersection there is empty. These sets are not two sets which live in the same universe. You can't take their intersection unless you're going to get the empty set. Really what I want to say is something like the set of all pairs where the first thing in the pair is part of F1 and the second thing in the pair is part of F2. Anybody know how to say that here? There actually is an easy way to say that with set theory language.
Would it be the union?
The union is also not quite right. Thank you for the suggestion. The union would be F1 union F2. Like in this example, the union is AD union with T. I mean, it would be this ADT. That would be the union. When really what I want is A comma T, D comma T, which is quite different from this is the union, which is not appropriate. You need something which is made up of pairs. Any other idea?
Is it the cross?
The cross, he says. Yes. Get rid of this. The cross, he said. Yeah, that's what the set theory product means. I can go F1 cross F2. That means the set of all pairs where the first thing is taken from F1 and the second thing is taken from F2, which is exactly what we wanted. All right. So this is how we write the product in terms of the set theory. Apart from the delta, like I said, is a little. It needs to be described kind of more specifically. Any questions about that so far, though? This is an example where actually describing the thing formally is actually very simple. I mean, I don't know how obvious any of this stuff was, but to write it down actually doesn't require any kind of fancy business at all. It's just a cross here, basically, and then, we'll have to deal with whatever the delta is. But in terms of explaining what exactly the product construction is, this is actually a very convenient way of explaining it. More convenient, I would say, than drawing the diagram. Okay, what about the delta? So to describe how the delta works, I have to somehow describe to you what if I have the delta looks something like this. The values of the delta must be described in terms of if I start at some state, which in this case is a product of is a pair of states, right? And then I read, say, the letter A, or it could be anything. I'm just using A as a generic letter. Then how do you say where it ends up? So I'm trying to explain the delta, remember, is basically describing where all of these arrows go. And the idea behind this is, for instance, this A arrow right here, what it means is when you start at C and T and do A, you get B and S. And the way you did that was by doing A from C and then doing A from T and just doing them in a pair separately. So what it means is the answer you get is really the pair of the first delta, which tells you that the C goes to the B, comma, the second delta, which tells you the T goes to the S. It looks like this. This also is not too complicated. Delta 1 of Q and A, comma, delta 2 of R and A. That says to do the delta of a pair, what you do is you just do the original first delta on the first thing and you do the second delta on the second thing and you combine them together in a pair. This is the description of the delta, all right? All right, that's the formal description of the product construction. And now that we have the formal description, remember I said last time the purpose of all of this formalism is not typically useful when it comes to writing down or drawing the diagram of a DFA, but the purpose of the formalism is so that you can prove things about the DFAs, which is generally impossible to prove things by just looking at the diagram. What is there interesting to use this formalism for the product? Actually, we can fairly easy, I don't know, you'll see how easy. I would like to actually prove that the language of M3 is really the intersection of the language M1 intersect the language M2, right? That's the whole point of all of this whole construction, is that this new machine that you get, its language is the intersection of the original two machines. That's why the construction is interesting at all. All right, and that you can prove using the formalism, and actually the proof goes fairly straightforward as long as you can stomach the set theory notations, which is a little taxing, I know. But anyway, can we just refresh our memories about the formal description of the language of some machine? So I'll just say, remember, the language of a machine in general is the set of all x in sigma star such that delta star of Q0x is in F. All right. This is one of the most cryptic bits of formalism that we've had, but this is a good sort of Hollywood style mathematics. You want to write stuff using tons of crazy looking symbols that has no immediately obvious meaning. This says the language of the machine is all of the strings. That's what sigma star means, all possible strings that you can make, such that the delta star means you start at start here, the starting state, and you read the whole string x, and the resulting state that you end up in is an element of f. That is to say, it is one of the accepting states. So this just says it's all strings x, such that if you start in the starting state and you read x, it ends up in the accepting state, or in one of the accepting states. So that's the definition of L of M. All right. Let's see if we can do this proof. So I'm gonna write. I'll write this as a theorem. Can I just say if M3 is the I will put this in quotes here, the product machine as above of M1 and M2, then this is the real theorem. The language of M3 is the language of M1 intersect the language of M2. That's what we're talking about here. All right. So remember, I'm just going to write out the details of the machines. So M1 is Q sigma delta 1 Q0 F1. M2 is R sigma delta 2 R0 F2. And then M3 is the product. That is Q cross R sigma delta Q0 comma R0 and F1 cross F2, where the delta, I'm just copying from what we wrote before. The delta is defined like delta of Q comma R, and A is the pair delta 1 of QA comma delta 2 of Q of RA. All right. And what we want to show is the language of M3 is the language of M1 intersect the language of M2. Let's just do it. Actually, there's no, as long as you're capable of following the somewhat thick set theory notation, there's no real big idea that you have to have. It's just a matter of rewriting the formalism. This is really the power of mathematical formalism, is that it can allow you to solve problems without thinking too much, just by like simplifying stuff or whatever. Let's do it. So the language of M3. First of all, I have to use the definition of the language of a machine, which you can see at the very top there. I'm going to do that, but using M3 instead of M. That's where I'm going to begin. So I'm going to start with the set of all x in sigma star. I'm copying. Can I scroll out a little bit? I want to keep it up there. A little smaller. All right, I'm copying the thing on top, but using M3. So x in sigma star such that delta star of now in M3 the starting state is Q naught comma R naught. So instead of this Q naught here, I'm using the appropriate starting states for M3 would be Q naught comma R naught comma X is in, and instead of F, the appropriate set to use in M3 is the accepting states for M3, which is this, F1 cross F2. So that is like so. All right, that's where we begin. And then the entire proof, like I said, doesn't actually involve any ideas. It's just a matter of rewriting the formalism in here. So the first thing I'm going to rewrite inside here is just this part, using the definition of delta. So this is what the definition of delta is. Now this is delta without the star, but actually the exact same formula works for the delta with the star. Remember, the delta without the star is what you do to one letter at a time, but the delta with the star is what happens to an entire string. But it's the same thing. An entire string, when you read from a starting point, it gives you a pair of these two things. So this becomes, I'm just going to say equals you know, most of this I'm going to copy, but I'm going to simplify part of it, and that is the delta part here. So it says, instead of delta star of that stuff, which this I think of as that, but I'm going to rewrite it as this. It's going to be a pair now. Delta 1 star of Q0x, comma. I'm basically just writing this stuff, but using Q0 and R0 instead of Q and R, and I'm using X instead of A, and the star, delta star instead of just delta. And then here, delta 2 star of R0X. Okay, that's that. Like so. All right, that was just the definition of delta star. Okay. Actually, that was the hardest step. The rest, that was using a definition of something. The rest is just pure abstract set theory. So what I'm going to do next is, this says this is a pair. If you look at where the parentheses go, that's a pair, and it's in this cross product. When I have a pair in that product, what it means is the first part of the pair is in F1, and the second part of the pair is in F2. That's what that means. So that's what I'm going to write. Next part. The first part of the pair is in F1, so that says delta 1 star Q0x is in F1, and the second part is in F2. Delta 2 star R0x is in F2. All right. And then there's basically just one step left, and that is when you see "and" inside the definition of a set, that means you could instead write this as the intersection of two sets. When you see the word "and" as part of the definition of a set like that, really what it means is this set that I'm talking about it's sort of the first part intersected with the same set with the second part. So I'm going to write this as an intersection. This is X and sigma star such that delta 1 star Q0x is in F1. Intersect X and sigma star such that delta 2 star of R0 and X is in F2. That is writing the set which has an "and" in it is the same as an intersection. I'm feeling pretty good about this. You remember where I intend to end up. I started with L of M3, and I'm supposed to end up with L of M1 intersect L of M2. And I have an intersection, so I like that. And what about L of M1 intersect L of M2? This, what this says, if you think about all of that business, it says all the strings such that delta 1 star, if you start at Q0 and you do the transition from the first machine, it is accepting on the first machine. Actually, this is, if you read the definitions carefully, this is L of M1. It's all the strings which are accepted on M1. And then what's the other one? It's L of M2. This is L of M1 intersect. And that's the end. All right. This may, by the way, I don't know if you have are starting to regret your life choices when you do proofs like this. This may be the only time that we're going to do a sort of big, long set theory proofs like this. This is not what the future of the course is going to look like for the most part. But every so often, it is important to do this kind of thing. All right. Anybody got any thoughts about that? This is using the set theory formalism. I said this is it's gonna be an easy proof. I don't know if this seems easy to you because the notation and is kind of thick, like I said. And if you look at this, it just looks to a passerby, it looks like a whole bunch of nonsense. But from the point of view of like abstract mathematics, this would be regarded as easy just because I didn't actually have to think any big ideas. It's just a matter of properly understanding the notations and playing around with the sets a little bit. All right. Okay, we got a little more than 10 minutes left. I think that's enough time actually to discuss the unions. We've spent all this time talking about intersections. So it is a fact. Maybe I'll write this as a theorem here. It's really the same as what I said before, but I'm going to say it in different language. Regular languages. This is the verbiage that we use to discuss this. Regular languages are closed under unions. Remember, closed under in this context means if I have two of those things, intersections is what I meant to write. I'm also going to talk about unions, but this is just summarizing what we've already did. Intersections. Regular languages are closed under intersections. That means if you start with two regular languages, then the intersection is also a regular language. Remember, regular language means it is the language of a DFA. So if you start with two languages, which you can do using a DFA, then the intersection is also something you can do using a DFA. All right. Okay, what about unions? Actually, unions we can discuss in our remaining 10 minutes. Doing a union machine is not really easier, but it's almost exactly the same idea as doing an intersection machine. So the same basic idea. It's not, of course, not exactly the same, but it's almost the same. The same basic idea can build a union machine. So I thought let's just do one example. To get the intersection machine, you do that whole product thing, and then you choose the accepting states to be everything which is accepted on the first machine and also on the second machine, right? That's how you get the intersection, by choosing the first machine and the second. But we can do the same thing to get a union if we just use or instead of and. So I'm going to say same product construction. I'll describe it in words and then we'll do an example and that'll do it. Same product construction for the structure of the machine, the states and the arrows and all that. But the accepting states are like pairs, something like, A, comma, T, where A is accepting or T is accepting. See, the one we did before, we said it was accepting when the first and the second are accepting, but that's because we wanted the intersection. If you want the union, you make it so that it's accepting when the first one or the second one is accepting. And then that gives you the union. You can, if you want to, prove this formally also, but it's the same proof basically. I don't want to go through the details. Let's just do an example, if I may. Let's try. I got M1s and M2s, right? Let's say M1 has STU like this. All right, there's my first machine, M1. And then I got an M2 here. Let's do VWX. W will be here. Oh, sorry, I copied the first picture again. I feel so foolish. Can you see I'm drawing the same one again? I zoned out in my mind a little bit. Sorry about that. Get rid of these arrows. It's that COVID again. That's one of the symptoms. Drawing the same DFA twice. All right, this is what I meant. I even put U at the bottom. I meant that to be an X. I'm losing it. And the accepting states are just X here. All right. I think this is what I wanted. Okay? So let's make a machine for the union. All right. What I said is we do the same product construction. That is, the structure of the states and the arrows is the same. The only difference is how we choose the accepting states. So I am going to make my pairs. I will start with S comma V because that's the starting states together. I think we can do this in 5 minutes. The A arrow from S and V, A goes to T here and A goes to X here. So that goes to TX. That's the A arrow. This is the starting state. TX, like so. From SV, the B arrow goes to U from S and W. So this goes to UW, which I'll put there with the B arrow. All right. I hope I'm doing good so far. The TX state from here, when I do A, T stays T, X stays X. So this is a loop like that. And the B arrow, T goes to S, X goes to V. So TX goes to SV, back to this starting state. Like that. All right, I like that. So what about the U and W? When I do A from U and W, it goes to T and W. So this is a new state. I'll put it over here. And the UW, when I do B, stays at U and stays at W. So this is a loop back like that. All right, and finally, TW, hopefully finally, I don't know, I might generate new states, but TW with an A becomes T and W, so this is a loop back here. And then TW with a B becomes S and W. That is a new state. Actually, I happen to know that's going to be the last new state. So this is an arrow like that. And then S and W, I need arrows here. S and W. With an A becomes T and W. That just goes back to here. And with a B becomes U and W. So that goes like that. And that's the end of my diagram, I believe. I only needed those 5 states out of a possible total of 9. Okay, and here's the important part. How do we get the union? What are the accepting states? So accepting any pairs where either one is accepting. So in the intersection machine, you look for pairs where both of them are accepting in the original ones. For the union machine, you look for pairs where either one or the other is accepting in the original ones. So that means in this particular example, I want any with either a S or a X, right? Because those were the ones S was accepting on M1 and X was accepting on M2. And so any of these states which have a S or X, those are going to be my accepting states. So in this particular example, this is accepting because of the X, and this is accepting because of the S. Right? And I think that's that. Anybody got questions about that example? So the union machine is really the same process as the intersection. It's just slightly different. The only difference is the accepting states. All right, and I think, and we got a few more minutes, but I think that's going to do it for me.